One of the things that a physics library needs, or a physics engine, is obviously going to be a good vector library, which is what I've made over here. Simple-vector.h. It's a single header file library that can basically manage any vector math for you. So as you can see, it has some very basic stuff, right? We basically need these two functions, right? Printf and square root. So we just make sure that if we can use them, then we include these two libraries that we need. Very simple. Then we check whether or not we've already included this vector header file. And this basically means, well, if we've already included it, then we don't need to have all of these forward declarations anymore, so we can just leave them out. We'll also use this SPL vector H definition basically later on when we are writing a matrix header library, so we can basically just create some functionality between a vector and a matrix depending on whether or not the vector library is actually active. Then all the forward declarations obviously get put into this. I might format them later so they're all nicely lined up. And also the naming is a bit, maybe not too smart. I should probably do something like SPL create factory empty or something like that, but for now it's going to be fine. So then what do we have in the library? Well, obviously we just have your basic vector object. Each vector is just going to have an x, y, and a z. These can represent positions. They'll probably just represent positions, or velocities, accelerations. They're going to be very widely used in a physics engine, right? Because you can't have any default values in C, I created a couple of functions that do this for me. Right, you have a create factory empty. This basically does is it creates a struct. We can go over it. It just creates a vector with all 0 values. Then the create vec3 basically just takes an x, y, and a z and creates a struct for you very easily. And then the last one is copy vector. Just pass it in a pointer to a vector object, to a vector struct, sorry, and you get a copy of the vector. Very simple stuff. Then obviously we also want to be able to do some very basic math operations with two vectors, which is what these 8 functions are for. These 4 over here will simply add or subtract, multiply or divide the 2 vectors that you give it, and then return a new vector from it, while these ones, the void functions, basically make changes to the first vector you give it, right? So we can demonstrate this. Right now, what we could do, for example, is just say add vector 3 v1 and then v2, and if we right now were to print out this v1 vector, you can see that it's no longer 1 2 0 but rather 2 4 0. Right, it makes changes directly to whatever vector you pass it in. Or you can also just say v3 equals get add vec3. If you right now were to print out this v1 vector and then also the v3 vector, you can see the v1 vector stays this exact same, while the v3 one is the result of the operation between these two vectors. So that's why it's not really necessary, because you can just clone the vector and stuff like that, but this makes it a little bit easier. Then there are the 2 limit functions. There are a couple of ways of limiting a vector, right? The first function, the limit vector 3, basically just constrains each component of the vector, right, the x, y, or z, between a minimum value and a maximum value, right? So these are just integer values. That's it. If it's under the minimum value, whatever component x, y, or z gets set to the minimum value, and the same for the maximum value, right? So pretty self-explanatory, the limit vector 3. Then you also have the limit magnitude of the vector 3. This again is also pretty self-explanatory. We simply get the magnitude of the vector, and if this magnitude is under the minimum or under the maximum, we just set the magnitude to the minimum or maximum. This can be very useful, especially the magnitude one, right? If you have some sort of object and you don't want it to have a velocity of 7 billion, you might want to just limit the magnitude of that vector. And again, it just makes the changes directly to the vector. So then there are the magnitude functions, right? This function over here just returns the normal magnitude of any vector you give it. And then as we'll see later on, we often need the magnitude of a vector squared. For that reason, it's also a function because it reduces the amount of operations we have to do. Then we also have the normalize function. Normalize function, as you might remember, it simply takes a vector and sets its magnitude equal to 1 while still pointing in the exact same direction, which is also very often used to set directions and stuff like that. And then obviously we also have a set magnitude, which, you know, it just sets the magnitude. So if we were to take a look at the normalize function, right, it just sort of gets the magnitude of whatever vector and divides each component by that magnitude, and then the set magnitude just normalizes the vector and then multiplies each component by the magnitude. Then we have a function called Getheading. What this will do basically, I actually haven't tested this one yet, but I don't see why it wouldn't work. It just returns the heading, right, the direction of the vector in radians. It can be useful if you have a car and you want it to point in the direction of the velocity, right? You can just get the heading of the velocity vector and then basically just rotate the sprite based on that heading. So then you also have the cross product and dot product functions, right? For here, cross product and dot product functions. They are pretty self-explanatory. The dot product simply returns the dot product of two vectors, while the cross product simply returns the vector, you know, the cross vector of two vectors, right? That's how a cross product is calculated. Just multiply the y times z minus the z times the y, and c times x, x times c, x times y, y times x, and I simply return a vector of these three components. The dot product is a lot easier, as you can see. You just multiply the x times the x of the other vector, and then the same for the y and z, and then just add all of these ones up. This is often used in I think in the separating axis theorem. The dot product is heavily used. Mod vector 3 just returns a vector that is basically the modulo of the two vectors, of a vector and an integer, right? So it's, and then the last function is the print vector3. It's very self-explanatory. It just prints out the vector, right? We've already seen this over here, print vector3 and print vector3. Just prints out the two vectors. So that's that for the vector library. So next time we'll create a matrix library, which are often used for transformations or what's it called, rotation matrices, or I forgot the name, projection matrices, which we'll also use. So yeah, hope you enjoyed.